Good morning, guys. Today we're going to be talking about the characteristics on and identifying function families. The objectives for today are identify family of functions, describe transformations of parent functions, and describe combinations of transformations. Remember that identifying function families, a function that belongs to the same family, share key characteristics. The parent function is the most basic function in a family. Functions in the same family are transformations of their parent functions. So basically what you're looking for is their characteristics. Usually families, I tend to say that they look alike. So if I want to look at that graph and see how it looks, if it looks alike, then it's part of the family, okay? Okay, here is the parent of the absolute value functions. Okay, the way you come to the graph is you actually have a table of values. Remember that an absolute value, when you put it in the absolute value, everything turns into positive. So if I have -6, that -6 will turn into a 6. The -4 will turn into a 4. This one will turn into a 2. This one 0, this one 2, 4, and 6. Notice they all come out to be positive. You need at least 3 points. You need the vertex, which is at 0, 0. You need -6, 6. So I'm going to take this one, which is here. Then I'm going to take this one, which is here. Once I do that, all I have to do is graph it. Notice it goes from corner to corner to the origin, and then from there it stays on the positive side. Notice the domain would be all real numbers, and the range, it goes from 0 up to infinity. So basically it includes that 0 and it goes up, nothing in the negative side. Okay, and that's what the graph would look for. Now if would look like if you have another absolute value function, well, you expect it to look like this because they would be on the same family. Okay, here are different functions. They're asking us to classify them, and in the test you're going to be asked to classify some functions like this. So take a look. Classify each function as constant, linear, quadratic, or exponential. Well, we know that the linear, of course, would be C, right? So this one would be linear. Oops, let me get my pen. Linear. This one, you should recognize this one. This one is your quadratic. That is the quadratic parent function. This is a constant because notice the number remains the same no matter what. Y equals 1 or f of x equals 1. So this is a constant. And this one then would be my exponential. And that's what they look like. Okay, take a look, review, and make sure you keep that paper that I gave you in class and review the different types of functions and what they look like. That's what you're going to be tested on. Okay, so we are going to start with the parent functions. Like again, we have the constant, as you see, the linear parent function, your absolute value parent function, and your quadratic parent function. They're equations, they're given equations. Make sure you learn them, and the domain and range of each one, okay? So take a look at those, study them, memorize them. We are given the first example identifying a function family. They gave us this one. Obviously, this one is the absolute value function. It looks like a V. Notice the absolute value sign on the equation. So the parent function, remember that it goes from corner to corner. So I'm just going to draw it here so that we could make a comparison. Looks like that. And what are the similarities? Well, the similar things that I could tell it's an absolute value function is because they both look like a V. Take a look, they're both opening up. Basically, one is narrower and shifted up. So if I'm going to compare the graph of f to the graph of the parent function, what you have here is that the parent function is wider than this one. So this one became narrower. The transformation it became more narrow or narrower. And also it's shifted up 1 unit. It's shifted up 1 unit. Notice how the equation changed also, and you want to notice or take a look at those changes. Notice that the parent function is f of x equals the absolute value of x, while this one is f of x equals twice the absolute value of x plus 1. Notice that twice made the graph narrower, and that plus 1 moved the graph up 1 unit. So similarities again, well, they have, they're both look like V's, and now this one is narrower and it's shifted up 1 unit. So the range will change. The range on this one, it goes from 0 to infinity, while the range on the f, the graph of f right here, goes from 1 to infinity. So that changed. Go ahead and pause the video and try this one on your own. And once you have identified what's different about it and what's the same about it and what is the family, then go ahead and play the video and it will help you, okay? This one is the graph of G. If I go to the parent function, remember my parent function is this one. It has a square. It looks like a U. So this must be quadratic. So now that I know that it's quadratic, I know the equation of the quadratic is f of x equals x squared. That is the equation. So that means if I do a table of values, remember that for x, if x is -2, then -2 squared would be 4. If x is -1, it would be 1, at 0, at 0, at 1, 1, at 2, 4. Now that I have those points, I could plot them. 0, 0, at -1, it will be 1. At -2, it will be 4. Then the same thing happened on this side. So it basically goes like this. I'm not going to be able to draw very well with this pen. I won't lie, but I'll try my best. So that didn't come out that bad. It looks something like that. So notice it's a U. Well, what happened? What is the difference? Notice this graph, the graph of G, became wider. It became wider. And also notice the vertex. The vertex shifted 1, 2, 3 units to the right. So the vertex shifted 3 units to the right and the graph became wider. Now notice the two things that change in the equation. Notice the graph of G. That equals a quarter of x minus 3 squared. So that 3 units to the right must be this number right here, -3. And that getting wider must be the factor right over here, 1/4. Now I wonder why I got wider, right? This is a smaller number. But we'll see that as we move along. So we are talking about transformation. A transformation, which is a new vocabulary word for you. Maybe you've heard it before, maybe you know what it is, but this is new vocabulary word for some people. Well, a transformation changes the size, shape, position, or orientation of a graph. Remember that a transformation can change the size, can change the shape, even the shape can change because it becomes wider, it becomes narrower. It changed the position, so a translation, right? Or orientation, there's a look up, there's a look down. A translation is a transformation that shifts a graph horizontally and or vertically, but does not change its size, shape, or orientation. Okay, so we're gonna go over example 2 here. They give us a graph, g of x equals x minus 4 and its parent function. So we want to graph these two. We want to graph g of x, and we want to graph the parent function. Then describe the transformation. Well, let's see. I know the linear parent function to be a line that goes from the origin and then it goes corner to corner. So learn those because the slope is 1 and the y-intercept is 0. So I'm just going to graph it real quick because I know where it is. See, if you learn your parent functions, then you could be fast about it. The next one is g of x equals x minus 4. Well, g of x equals x minus 4. That means that this graph is a translation 4 units down. So I know that my y-intercept is -4 right over here. And I know, oops, let me go back on that. It's right here. And then I know that the slope is 1. So 1 over 1, just like the parent function. So we'll go corner to corner. So at this time, I could draw my line and make a comparison. There we are. Okay, so now that I drew my line, I noticed that the line is moved down. So the comparison is that this line moved down, and when it moved down, it also appears to move to the right in this case. See, it moved down and it also appears to move to the right, but in reality what is happening is that it's moving down. I could actually grab it here and notice as I move it down, this side right here appears to be moving also because the slope didn't change. So that is a translation or a shift, but we're gonna call it by the right word. That is a translation 4 units down. So you could write that down. It's a translation 4 units down. Okay, very well. Another transformation would be a reflection. A reflection is a transformation that flips a graph over a line called the line of reflection. Like when you look at yourself in the mirror, the line of reflection will be that mirror. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So again, when you look at yourself in the mirror, like if you look at your nose, it's exactly the same distance, but on the other side of the mirror. And every point in your body is exactly the same distance on the other side of the mirror. That's why it's called a reflection of yourself. Okay, so let's look at example 3. Graphing and describing reflections. Let's look at what they would look like. Okay, here we have the graph of P of x equals the opposite of x squared. You could say that P of x equals the opposite of x squared, or P of x equals -x squared. Whatever you want to say, it's correct. And its parent function. So let's graph the parent function. The parent function is here, y equals x squared, while the opposite is right here. The opposite of x squared is right here. Notice that the opposite means that the numbers just become the opposite. If this one was 4, this one is -4. If this one is 1, this one is -1. So this is the output. Okay, this is your y, your output. This is your y for x squared, and this is your y for the opposite of x squared. So let's graph them and see what they would look like. Well, we know we have one point at 0, 0. Then we have a point at -2, 4. So -2, 4 right there. It's like playing bingo, guys. Or if you play loteria, then you know what I'm talking about. -1, 1 right there. And then we have at 1, we have 1 for the first one. And then at 2, we have 4. So it would look like that. If I plot the next one is for -2 is -4. So let's use another color. For 0, 0, for -2 is -4. Notice it's the same distance. Notice this is 4 units up from the x-axis. This one is 4 units down from the x-axis. So this one is 1 unit up from the x-axis. This one will be 1 unit down from the x-axis, and so forth. Once I draw them, you could see, and I'm gonna try to draw them here. Please don't judge me. Look something like this. Something like that. And then we have the other one. The other one will look something like this, right? And notice the reflection. Notice one is a reflection of the other across the x-axis. So this is what a reflection would look like. Anytime you have something flip, that transformation is called a reflection. Go ahead and try these 3 and describe the transformation. Draw the parent function and draw this graph and compare them both and describe the transformation. Pause the video, try to do it on your own, and then come back and see how you did. Okay, so let's do it. I noticed the first one we have is a linear function. The parent function for a linear function is y equals x. So I'm going just to draw that line because I know where my parent function is. Again, if you learn your parent functions, it will be easier for you to get this done. So x plus 3. So I know from algebra 1 that basically this is a shift up 3 units. So basically the y-intercept now is 3. The slope's still the same. So my other function should be over here. Let's see from here. I want to just draw it from corner to corner because the slope's still 1. All right, so now that I drew it, 1, 2, and 3, because the slope is still 1 over 1, and the y-intercept is 3 right here. Notice what happened is a translation of 3 units. This is a translation of 3 units. So I'm gonna just write that down. Translation. Oops, another one. Translation up 3 units. Notice that when it goes up, it also appeared to move left. Notice it, in this case, it moved left 3 units as well. This one is the quadratic function. I already know my quadratic. So it's a 0, 0, 1, 1, and 2, 4. And it will reflect on the other side this way. So the same distance from the axis of symmetry. You learned that in algebra 1. So let's draw that one. So I'm going to try to draw it the best I can. All right, goes like that. Oops, my line there kind of got messed up, but it looks something like that. Okay, so what happened to this one? X minus 2 squared. Okay, so let's see if I give values to x. If x would be 0, so if I put 0 over here, if I put 0, 0 minus 2 is negative 2, and negative 2 squared is 4. So if I put 0 right here, then it would be at 4 right over here. So I'm gonna just plot that point. So it would be there. If I put 1 over here, 1 minus 2, 1 minus 2, it would be negative 1. And negative 1 square, it would be 1. So at 1, it would be over here. Then at 2, 2 minus 2 is 0, and 0 square is 0. So at 2, the output would be 0. So it would be there. And now I could see that that's the vertex, because then I go to 3. 3 minus 2 is 1, and 1 square is 1. So at 3, it'll be a 1. So notice my graph. So at this point, this is my vertex. So 2 that way, I am good to go. So now I could see what the graph looks like. Right, do something like this, something like that. So notice what happened is a shift or a translation 2 units to the right. So this is a translation 2 units right. And then we have the absolute value function. The absolute value function, notice this is the opposite of the absolute value function. I think we did that already. Basically, the absolute value function, the parent function, I know what it looks like. Here it is. And then the opposite of that would be on the other side, right down here. So I'm just going to change my line to different color. And I'm just going to continue this line. And do the same on the opposite side, because that is a reflection across the x-axis. So at this point, I do my reflection, and then describe it. This is a reflection. This is a reflection across and x-axis. I'm gonna put it down here, x-axis. All right, I hope you did good on that. Another type of transformation is your vertical stretch and your vertical shrink. Remember, in the vertical stretch, it gets narrower. So let's write that down. It gets narrower in the vertical stretch. While in the vertical shrink, it gets wider. Think about a gummy bear, right? If you shrink it, if you squeeze it down, what's gonna happen to the gummy bear is gonna get fat. It's gonna get really fat. This is gonna try to expand. But if you take that gummy bear and you pull it up, but hold it so it doesn't move from the bottom and pull it up, what is gonna happen? It's gonna get narrower. Well, the same thing is happening to the graph. The floor in this case is your x-axis. If you pull away from the x-axis and it appears to get narrower, that means you have a stretch. If it appears to get wider, then you have a shrink. Let's take a look at that. Here is an absolute value function. The parent function would look like this. Remember, it goes corner to corner. That's your parent function. Okay? Now, this one is 2 times the square, times, not the square root, I'm sorry, 2 times the absolute value of x. So if x is 0, then the absolute value of 0 is 0 times 2 is still 0. So I'm just going to plot the point. Let's see. Let me get my pen. I plot a point at 0, 0. Then if x is 1, let's pick it over here. If x is 1, then the absolute value of 1 is 1 times 2 is 2. So at 1, it will be here. So that means at -1, it will also be here. Then if x is 2, well, 2, the absolute value of 2 is 2 times 2 would be 4. So at 2, it would be at 4. Right up there. So on this side, at -2 will also be there. Now I could draw my lines and take a look at what happened. Notice how the graph became narrower. I wish I knew how to draw, because I could make it that if you have a guy here, let's say, let me put it like this. You have a guy here. He's standing right here and he is pulling. You know, he has his hand and he's pulling from here and he's pulling up. So he pulled this and he pulled this one up that way too. And there is the guy pulling the ropes and pulling it up. As he pulled these up, notice it gets narrower. That's why it's called a vertical stretch. Because he is pulling up. See how these move? All right, so let's take a look at this quadratic. I wish it was the same one because it's easier for me to draw, but let's take a look at the quadratic. In the quadratic, we have the parent function. Parent function looks like this. I already know what it looks like. So basically, I will have something like this, right? Okay, so what happens if I say 1/2 x squared? Well, if x is 0, let's change color. If x is 0, then 0 times any number is still 0. So that would be there. While if x is 1, well, 1 squared is 1, and half of 1 is 1/2. So I will have a point here, and I will have a point there. If x is 2, 2 squared is 4, and half of 4 would be 2. So I would have a point here, and I would also have a point here. If x is 3, 3 squared is 9, and half of 9 is 4.5. So I would have a point at 4.5. So I would have a point there and a point there. And notice what happened. Notice how the graph got wider. So it's like if you have somebody here with his legs pushing down. That's his legs, right? And he is pushing it down. He's pushing it down. So because he's pushing it down, that's called a vertical shrink. Okay, I hope that was a good example for you. Okay, it's your turn. This time you try these three graphs. Go ahead and draw them and their parent functions and make a comparison of what happened. Okay, the first one, make sure you stop the video before you look at it, so see how you do. The first one is a linear function. So the parent function basically is corner to corner again, going through the origin. Now this one, the y-intercept is still at 0. The y-intercept is still at 0, but notice the slope change. The slope changed to 3. So rise over run, 1, 2, 3 over 1. So that this is the other point right here. And another point would be if I go down 3 and I go left 1. There is the other point. So my line would look like that. So at this point, I just draw my line. All right. There. I think it goes. Something like that. Notice how what happened was the guy from up here pulled. He pulled up. Since he pulled up, he pulled this line up. That is a vertical stretch. So my answer would be this is a vertical stretch. Then we have the quadratic. In the quadratic, we have point there, point here, point here, point there, point there. Okay, let's draw it. And this side. And now we just have to, in case you're running away from this one, don't be afraid because it's a fraction. Because if you do a table of values where x and y, right? If x is 0, any number, if 0 squared is 0, any number multiplied by 0 is still 0. So I would have a point right there. And then if x is 1, 1 square is 1. 1 times any number is that number, so that's 3/2, or 1.5. The same 3/2 is 1.5, okay? Now, if x is 2, well, 2 squared is 4. 4 times 3 is 12. 12 divided by 2 is 6. So that means that's 6. So let's plot this point. 2, 1 is 1.5, so it should be right there. And at 2, it should be 6, so it should be up here. Now that I know that, I could put a point here. Notice the same distance right there, and then here is the same distance, so it would be about there. Now I could draw it. And please don't mind that, because I can hardly draw straight from here. Well, what I noticed, it became narrower. Since it became narrower, that's because this is not a true fraction. This is a number bigger than 1. And if the number is bigger than 1, it's going to become a vertical stretch. So this is still a vertical stretch. So I'm just going to write that down. Vertical, copy that. So copy and paste. Aha. I love this. Right? Now I can do that. That's a vertical stretch. This one right here, notice the number right here, that factor is less than 1, And since it's less than 1 more than 0, that's going to be a vertical shrink. But let's look at it. So we have the absolute value function. Parent function is here. Okay, so this one is 0.2 times x. So if x is 0, that means that the output would be 0. If x is 1, that would be 0.2. If x is 2, it would be 0.4. If x is 3, it would be 0.6. If x is 4, it would be 0.8. If x is 5, it would be 1.0, so it would be here. So it would be also here at -5, it will also be 1. So now that I have that, all I have to do is draw my lines and see that that is a vertical shrink. Notice how the graph got wider. So that is a vertical shrink. Okay, so how you do? Hopefully you did well, if not corrected and well. Okay, here is our last objective, a combination of transformation. Instead of just doing one transformation at a time, we're gonna do a set of transformation and describe that combination of transformations. Look what happened. Use a graphing calculator to graph g of x equals the opposite of x plus 5, or I'm sorry, the opposite of the absolute value of the sum of x plus 5, and then take away 3. And its parent function, then describe the transformation. Here is the solution. Actually, notice that that negative, we notice that it would do a reflection. This one, it would move the graph 5 units to the left. Instead of moving it to the right, when we're talking right or left, it's inside the parentheses. It is the opposite of what's happening, and I will explain that later on a later lesson. And then this -3 out here, it would move the graph down 3 units, okay? Let's take a look at how that happened on the calculator so you could see the different moves, okay? Here we go. Add graph. So the absolute value function, I go here, I press absolute value, and that's the absolute value of x. I go ahead and graph it. Take a look at my graph. This is the graph f of 1 or f1. Let's make another graph. Let's make f2, and let's make it exactly the same so you could see the different transformation, okay? This is the graph 2 or f2 of x equals the absolute value of x. Notice it's gonna go on top of the first one. Now let's start the transformation. If I reflect it, that means I'm gonna put that negative sign right here on top, in front. So I'm gonna go ahead and press the tab key, go back to the graph of 2, and go in front of, and put a negative sign. And notice when I do that, what happened to the graph? The transformation was a reflection. Now I want to move the graph left 5 units. So in this case, I want to go back to that graph, tap, go up to graph 2, and then inside of the absolute value, I'm going to put +5. If I put -5, it will move to the right, so +5. That would move left 5 units. So I press enter. Notice what happened. It moved left 1, 2, 3, 4, 5. Then I want to move it down. I want to move it down 3 units. So I go back to that graph, and this time outside, I'm just going to put -3. Press enter, and notice how it moved down 3. And basically, that's exactly what they're showing you here, except that in this one, it goes by 2, 4, 6, 10. So that's why it doesn't look like it's 5. That's because the scale is different. The scale is 2, 4, and then 5. See, 5 units to the left, 3 units down. 2, 1 is 3 right there. Okay, I'm gonna go ahead and finish the lesson right here. Make sure you go and do the assignment, which is already on your assignment in Big Ideas. So have an awesome day. I'll see you back in the classroom.